So, this third lecture, let's start with some plan and some reminders. So, we have done up till now basically a review of the basics of two-dimensional CFT. And let me remind some very important results, well, results we will use today. So, first, we have this degenerate fusion products of representations of the Virasoro algebra. So we know that when we fuse the degenerate representation, which has a vanishing null vector level 2 here, like R21, with any Verma module, we'll find a sum of two terms. So two other Verma modules, and we know the momentums of these two Verma modules. So this must apply also to operator product expansions of the corresponding fields, of course. So this fusion rule of representation is a simple way to encode constraints on operator product expansion. Then we move to non-chiral CFT, meaning to coupling the left moving Virasoro algebra with the right moving Virasoro algebra. So fields now have a left and a right conformal dimension. And we have extra constraints that come with that. I mean, the constraints that are correlation functions basically are single value. And in particular, we could derive the two-point function. I mean, based on the conformal symmetry, we had an undetermined factor called the two-point structure constant, V here. And we have a factor completely determined by conformal symmetry, starting with a delta function, which obliges the conformal dimensions of these two fields to be the same, both on the left and on the right, and then a dependence on Z, which is what it is. And here I'm using my infamous modulus squared notation, which is not really the complex modulus squared, but which just means taking this quantity and multiplying with the same quantities with bars, except that Z bar is the complex conjugate of Z, but delta bar is not the complex conjugate of delta. It is just the right moving dimension. Okay, so based on these results and ideas, we can start really constructing exactly solvable CFTs. But before doing that in examples, I started with some structural generalities. In particular about the spectrum. So I was trying to define the various types of spectrums we can have. And well, one important object is the OP spectrum. So when you do an OP of two fields here, so let S1 to be the set of primary fields which appear in this OPE. And well, we want the spectrum of our CFT to be closed under OPEs, meaning that if I and J belong to the OPS is the spectrum, the whole set of the fields in our CFT of primary fields, and we want any Sij also to be included in this set. So we do an OP of two fields, of course we should remain inside our CFT, but then if this allows us to define extended spectrums, so long as this condition is still obeyed, we can add extra fields, but we have to add whatever comes out of their operator product expansions. Okay, so are there questions about that? So if not, let's discuss a bit more which fields we want to include in our model. So we'll start with degenerate fields. Well, but before that, I have to mention an important point, which is and to define what are diagonal fields. So based in particular on this two-point function, if we want this two-point function to be single-valued, we have a constraint now on the dimensions. So the left and the right dimensions, so their difference, which is called the conformal spin. has to be half integral. So when I'm building a field, I have to satisfy this condition. And well, the simplest way to satisfy it is probably that if their dimensions are equal. So a field which has equal left and right dimensions is called a spinless field. Well, a field whose spin is 0. Well, sometimes in the literature it's called a diagonal field, but now I want to define a slightly different type of diagonal field. So, because the degenerate fields play a very important role in exactly solvable CFTs, so what matters is not just that the spins are equal on the left and on the right, but also if they remain equal after I'm doing an OP with some degenerate field. So let's say that if V is spinless, but also if in this OP of any degenerate field, in fact, with V I find only spinless primaries, then by definition I am calling V diagonal.
These with the degenerate V's, they are not chiral. They are.
Well, for the moment, I mean, we'll see in an instant. I mean, we'll assume that they are in fact diagonal themselves. But
if not, you have little chances to find spinless fields on the right, isn't it?
Right.
Okay.
Complete now. I mean, it's no more the chiral fusion rule, which.
Yeah, now I'm talking about really the fields, so which have a left and a right dimension. So there is this slight subtlety between spinless and diagonal. Okay, but it doesn't really affect the definition of a diagonal CFT. So a CFT is diagonal if all primary fields are spinless or diagonal. I mean, it's equivalent, you know, that all of them are spinless or all of them diagonal. Okay, so diagonal CFTs are, well, they are simpler. So we'll start, in fact, when it comes to building examples, we start with diagonal CFTs before moving to non-diagonal CFTs. Okay, so now which fields do we allow in our CFT? So we start with the degenerate fields. And by degenerate, I mean diagonal and degenerate. So a field which belongs to a degenerate representation here on the left, but also the same degenerate representation on the right. So let's see, these are fields in the first column and the representation of the conformal algebra then. Okay, so these fields are supposed to exist for R and S positive integers. I mean, and well, the central charge for the moment is anything. And their conformal dimensions, left and right, well, by definition, they are delta RS and delta RS, the same on the left and on the right. Okay. So next, which other types of fields could we have? Well, there is a distinction between fully degenerate and degenerate fields. So let me mention the fully degenerate fields, VFRS. Well, they belong to fully degenerate representations, of course. So the distinction between degenerate and fully degenerate makes sense only when the central charge is rational, when beta squared is rational, in fact. because this is a necessary condition for having several null vectors in the same representation. So if I have several, I can decide if one of them vanishes or maybe all of them vanish. So all of them means it's fully degenerate, but if only one of them vanishes, I have just a degenerate field. So again, the conformal dimensions on the left and on the right are the same. And R and S are still integer. Okay, so then let me define a diagonal field here. The P is labeled by its momentum. So momentum is related to the conformal dimension by this formula. So this one would have the dimension, so C minus 1 over 24 plus P squared, both on the left and on the right. So at the moment, P is any complex number. And so this field belongs to the Verma module on the left and on the right. Okay, and finally, let me introduce non-diagonal fields. So all these fields so far are diagonal. So the non-diagonal fields. So now the non-trivial point is that instead of labeling them with their left and right dimensions, I want to label them by indices R and S, such that the left dimension is delta RS and the right dimension is delta R minus S. So I'm allowed to do that because I mean they depend on two numbers, the left and the right dimensions, and I'm allowed to rewrite these two numbers instead of two other parameters, these cat's indices R and S. So these parameters for the moment are just any complex numbers. And this is a notation which will be very convenient, as we will soon discover. And then my non-diagonal fields belong to, in general, to Verma module, V delta S times V bar delta R minus S. Well, there are exceptions to that, but I mean, if R and S are, let's say, if R and S are integers, non-zero integers, then, well, in one of these Verma modules, you will find some null vectors, and then you have to decide if they vanish or not. So the structure can be more complicated in these cases. But in general, it's just Verma module. Okay, so these are the fields from which we want to build some non-trivial and unsolvable CFTs. So let me say a bit more on the non-diagonal fields. So in particular, I mean, it's important that the spin is half integer for single valueness. What is the spin of a non-diagonal field? So that's delta Rs minus delta R minus S. So let's call it SRS. So which is P squared Rs minus P squared R minus S, which is, well, P, so the, okay, let me do this calculation. PRS minus PR minus S, PRS plus PR minus S, which is P 0 to F, P 2R 0, which is minus RS. Okay, so the spin of a non-diagonal field is just the product of these two indices, and this we want to be half integral. Okay, and then let me just point out that this parametrization of fields is a bit redundant because I'm using here the momentum in particular P, but the conformal dimension is P squared. So we have relations like Vp equals V minus P, but sometimes it's convenient to allow for non-trivial reflection coefficient Rp. And similarly, in general, we have when VRS equals V minus R minus S.
Is it just a number? R?
Sorry, R and S. RP, yeah, it's just a number. It should not depend on Z. It's not a field. It's yeah. It's called the reflection coefficient. Well. Okay, so the next question is
somehow you could have several fields with the same P in your theory, isn't it? So then you could imagine having a matrix or whatever.
right. So it could be that that my fields are not completely defined by the conformal dimension. I would need to add extra indices or something to distinguish fields with the same dimension. Yeah. Okay, so let's start with the diagonal fields. So which diagonal fields will we have and how many will we have? So we want our spectrum to be stable, well, closed on the OP. So if I start, for example, with V12, and then I'm doing OPs. So, well, we know what is the fusion product of R12 with itself. So it gives us R11 plus R13. So V12, well, it can contain V11 plus V13. So in fact, we assume that both of them are there for the moment. So everything that's allowed, let's say by the fusion rules here, appears actually in the OP. So if that's the case, then if I do repeated OPs of V12 with itself, I will generate a family of degenerate fields. So let's say from V12 alone, I would generate, in fact, all the V1R with any R V1S, sorry, with so an infinite family of degenerate fields. Well, if I started with the trivial field V11, I would just keep with V11, which fuses to itself.
Is there also the possibility you take the OP of V12, V12? Can't it also contain something non-diagonal, which looks like 1, 1 on the left and 1, 3 on the right?
No, in fact, in general, not. So first, I can get only something degenerate because degenerate fields fuse to other degenerate fields, and right, if you try to have V11 on the left and V13 on the right, the spin in general is anything. Well, it depends on the central charge. So
for some central charge, it's going to be an integer.
Yeah, right. It could happen. Accidents could happen. So here I'm assuming the central charge is generic and there is no accident. So using degenerate diagonal field, I only get degenerate diagonal field. Okay, so from V12 I generate all these. So if I start with V13, well, I would generate again an infinite family of fields, but only with odd indices now. So fusing odd, I mean, odd with odd remains odd. Or I could have several degenerate fields. I could start with V12 and V21. And then I would generate the whole set of degenerate fields. So there are only 7 possibilities actually, modulo the exchange of R and S. Yes?
Sorry for the weird question, but are we, maybe I missed it, so the spin is quantized? So is that so far an assumption, or are we thinking of motivating that in terms of some symmetry? Like sometimes you say, okay, modular invariance imposes spin quantization.
So here the motivation is single valuedness of correlation functions.
Okay.
So it's an assumption that you can relax,
Okay.
but I mean we don't really want to relax it.
Okay. No, it's good. So single valuedness imposes spin quantization. Okay.
Okay, so I was in the process of enumerating basically the families of degenerate fields that are closed on the fusion, and there are in fact only 7 families modulo the exchange of R and S. So here are 4 families, and if you, I mean the remaining families, they would be generated by V12 maybe and V31. That's when the second index is anything but the first has to be odd. Or you could have V13 and V31. And 1, 2, 3. Oh, I'm missing one family here. Well, yeah, I'm missing a trivial family where we don't have any degenerate fields.
So is 7 possibilities are an answer to which question exactly?
Well, what is the set of degenerate fields in our CFT?
So
We have to pick one of these
we
7.
have a CFT, which we assume that has at least one degenerate field.
Yeah, so, but in fact, we'll work with only 2 possibilities now.
When you act on VRS with this degenerate V12 or V21, you remain in this field RS. You don't change the class of. I'm confused.
Well, that's a very good question, but we are. I mean, you mean non-diagonal fields?
Yes.
No? Yeah, but we are not there yet. First, we determine which degenerate fields exist, and then we'll see what happens if you fuse it with some other field.
There is no V1. It is not possible to avoid having V12 or V13.
Yeah, right.
There's just some VRSB, and there's just no constant.
Right. If you start with some VRS with high R and S, and you start to, let's say if S is odd, you'll end up with V13 basically. And if it's even, you
by doing OPs.
Yeah, by doing OPs.
It's just the same rules as spin. I mean, if you start with spin, we can have half integer spins or integer spins, they remain together. But then if you start with 2 high spins, you will create all the ones that are downstairs.
Yeah, exactly. So, okay, so for us, we will really work with 2 possibilities. So, CFT with 2 diagonal fields, with 2, degenerate fields. So by definition, this is a CFT which contains V21 and V12, and therefore, in fact, all the possible degenerate fields. And CFTs with 1 degenerate field, by definition, we take it to be V12. Now, of course, there is the other possibility that it could be V13 here instead of V12, but it doesn't matter so much. I mean, I'm not assuming these fields are in the physical spectrum. I'm only assuming they exist, so they are in the, let's say, some extended spectrum.
I still don't quite understand the previous answer. So just because some V is allowed by representation theory to appear in the OP of 2 field, it doesn't mean that it actually appears, right? It doesn't mean the 3-point function is non-zero.
Yeah, right. You're right, but I'm assuming it appears, so it's a new axiom. I mean, I'm allowed to add axioms as I go, basically.
So there could be, in principle, CFTs that only have some VRs with high R and S and no smaller.
Yeah,
No smaller R.
Yeah, it's conceivable. And to some extent, it exists if you look in E-series minimal model. But I won't talk about that. So indeed, my axioms apply to some class of CFT, and as always, if you relax them, then you can get more. Okay. So, I mean, the existence of these degenerate fields will really determine the structure of our CFT. So, it has even been proposed that I should add these degenerate fields to the symmetry algebra. So our symmetry algebra for the moment is made of it's a conformal algebra made of Virasoro left and Virasoro right. So if you want, it's generated by the left and right energy momentum tensors. But the suggestion is that we could define an interchiral algebra where you would add maybe V12 to this symmetry generator. So you would consider it a symmetry generator. Well, so the interchiral algebra is not really an algebra, but the ideology is that it plays the same role as an extended symmetry algebra. And in fact, you can even define interchiral conformal blocks by summing a series of Virasoro blocks. So I will not use this interchiral language, but I just mentioned that it exists.
Why is it called interchiral?
Well, because this V12 is not chiral, it's the same on the left and on the right. Okay, so now the next question is to what happens if I have some diagonal fields, say VP, and I'm doing an OPE with, let's say, V12. So by the fusion rules, which are still there, I can get, how many do you think I can get? How many fields maximum could I get? Two? Well, in fact, 4. Because the fusion rules apply on the left and also on the right. So I could get some field with the left moment to P minus beta over 2, and right momentum, well, here it could be P plus minus, and on the right also P plus minus. And sorry, it's 1 over 2B. I have these 4 possibilities. But now I have to look at the conformal spins of these fields. So, well, first I have fields which are themselves diagonal. So, Vp plus minus 1 over 2 beta. By this, I really mean one of these fields with the same dimension on the left and on the right. In which case, I have no problem. The spin is 0. But I could also have fields, the other 2 fields, they are not diagonal. And in fact, their spin typically is not half integer. So I have to eliminate them. So in fact, I only have these 2 terms. And similarly, if I do this OPE, I must get just these 2 terms. Okay, then let's mention what Vincent was asking for, the non-diagonal fields. So V12, VRS equals what? So how many possibilities do we expect? Well, again, 4. 2 on the left and 2 on the right. So now the trick is to write these 4 possibilities again in this notation. And if you do that, you'll find, well, 2 possibilities of this type are S plus or minus 1, and 2 possibilities of this type, V R plus or minus beta minus 2 S. So let's say for the moment these are just possibilities. It has to be included in this. So now can we allow all these fields to appear? So we have to look at their conformal spins. And in fact, more precisely, we look at the difference between the spins on the right and the spin on the left, because all of them have to be half integral. So the spin of this field, let's say f plus 1 minus spin Rs, well, it's pretty easy to compute if you remember that the spin Rs is just minus Rs. So the spin difference should be minus R. And then the spin difference for the other one, plus beta minus 2, S minus S, it should be minus S beta minus 2. So if we wanted all these 4 fields to appear, we would need that R is half integer, S beta minus 2 is half integer, and also RS is half integer. Well, if you combine these three conditions, you'll find that beta minus 2 has to be rational. Right? Because beta minus 2, yes?
S should be in the S beta moins 2.
Well, maybe let me do it. Well, basically, or maybe you just remark R is rational, RS is rational, so S is also rational, and then S beta minus 2 is rational, so beta minus 2 is rational as well. But we don't want that. I mean, we want to keep beta squared generic. And so this forces us to choose between these terms and these terms. And this choice is just a matter of convention, but of course my conventions are that this is the simplest formula, so we eliminate these terms. And we are left with V12 S equals sum VR R S plus or minus 1. And similarly, V21 VRS equals VR plus minus 1. Yes,
could you imagine a conformal field theory for which you would even decide that R is not a half integer, RS is a half integer, and so your field VRS is fine, but R is not a half integer or whatever, so you have nothing on the right.
Yeah, probably it would not be a very interesting conformal field theory, but you can imagine it. Yes.
Well, it's a generic case, isn't it?
But if you have nothing, it means basically that it decouples. So your field V12, if it decouples, it's as if it was not there. So fine. So then you get a CFT, but without degenerate fields, with current technology, you can do little about it.
When you add this plus, it means it doesn't necessarily have this filter in the fusion rules. I mean,
yeah, it doesn't. It means they are the only filters. But no, I'm also assuming that they do occur. This one? Well, it's doing the same exercise, but with V21 instead of
V2. Oh, V21. Okay.
Yeah,
I thought it was.
Okay, and let me remark also that by allowing these fields, I also got some conditions on R. So here R has to be half integer, and here it's S which has to be half integer.
But you also want spin to be half measure, so also S.
Yeah, indeed, I also want the spin, so I want here, I still want RS to be half integer. But this allows S, the second index, to be fractional. And here we start to see the spectrums of, let's say, the Potts model or the ON model to emerge.
Why do you insist on working on generic data? It's one of the most interesting models have a very specific data, which is often actually rational or beta squared.
Yeah, so that's a good question. The point is that rational values of beta squared are very hard. So you get all these possible complications because now we possibly have more terms in these types of OPEs, but it depends on the values of the parameters, which terms you have. So everything gets more complicated. So the ideology here is that we'll work at generic central charge, and then if we are interested in specific model, like percolation, we'll take a limit. And the complications will appear in the limit.
if you imagine you have models where you can follow beta continuously.
Right, I want beta to be a continuous parameter. It's the case, in fact, in the, let's say, Potts ON models and all these loop models. And in fact, yeah, even the structure of representations is much more complicated for rational beta squared because you can have several null vectors, in fact, infinitely many null vectors in the same Verma module. So everything is simpler in the generic case.
You can recover this this fact from representation theory by taking a limit for a continuous beta?
Essentially, yes. So at least today we plan to recover the fusion rules of minimal models from the generic beta fusion rules.
So you can take beta, let's say, such that the suppose you take central charge larger than 1, generic, or well, just generic, and then, you know, by setting it to a specific value of the minimal model as a limit, you can recover the fusion rules of minimal models.
Yeah, that's what we'll do later.
Could it happen that what you crossed somehow suddenly happens when you go to a rational value of beta?
Yeah, it can come back, but typically it will come back from elsewhere in the spectrum, in a sense.
But could you explain why it doesn't matter what exactly you cross when you cross the first term?
Well, these two terms are incompatible because if I assume both of them, it implies that beta is
Yeah, but you said that it doesn't matter which one.
Right, it's really a matter of convention, in fact. But just because if I choose only one term, it can happen for, well, generic beta squared, so I'm fine.
You make several choices of that kind. It's unclear for me that you couldn't do one choice for one fusion rule and another choice for another one.
Right, so this is an extra exercise which can be done. But indeed, these two choices, if you want, are compatible, but they are also correlated. Okay, so now let's go slightly further. So we know that R is half integer, and then let's look a bit more at this OPE. So in this OPE we have now if we take the field at Z and the other field at 0, we have coefficients here which depend on Z. So Z to well let's say delta RS plus 1, if we consider the first term in this sum, minus delta 1, 2, minus delta RS, and we have a Z bar, delta R minus S minus 1, minus delta 1, 2, minus delta RS, and Z RS plus 1. So I'm just considering this term. And then I want to look at the monodromy of V1, 2 around 0. So the monodromy is determined by the speeds. So the difference of these dimensions is determined by this spin difference, SRS plus 1 minus basically SRS. So here it's a minus S. Well, this we computed already, it's minus R, which means that the monodromy here is e to the 2 pi I R. So this can be 1 or minus 1. So if R is half integer, we have a non-trivial monodromy, which means the correlation function is not really single valued, it's double valued. So let's say that's fine, that's a reasonable relaxation of our axioms. However, if we consider some endpoint function, VRI SI, and then we make V1, 2 go around all the other fields, well, the product of all the monodromies must be 1. And so product e to the 2 pi Ri is 1. So this implies, well, let me write it here, that R the sum of the r's should be integer. So basically r is, it can be half integer, but it has to be conserved modulo integers. And similarly, in the second situation, the index s will be conserved modulo integers. Okay, so to finish this, well, these generalities about solvable CFTs, I want to say something on the convergence of OPs. So, let's imagine we have some OP V1, V2 equals the sum over the spectrum of primary fields Vk. So for this to converge, basically we want the conformal dimensions of these fields to be bounded from below. So more precisely, we want the inf over this spectrum of the real part of delta k plus delta bar k to be more than minus infinity. Okay, but now if we have this field V1, 2, and if we have fields, some fields, a non-diagonal field VRS, well, by doing repeated OPEs, I will get values S plus L, let's say, or L, well, any, in fact, any integer number. So I will get this infinite sequence of fields. So what I mean is I will get VRS plus L. So in this infinite sequence, I want the total conformal dimension to be bounded from below. And well, I have to compute it. So delta, so the conformal dimension of a non-diagonal field is delta RS plus delta R minus S. And from these formulas, you can compute it. So C minus 1 over 12 plus 1/2 R squared beta squared plus S squared beta minus 2. And now we see that the second index L, well, it can go to real infinity, basically. So S squared can go to plus infinity. And so if I want this to be bounded from below, I have to assume the real part of beta minus 2 to be positive. Well, that's equivalent to real part of beta squared positive, or in terms of the central charge, real part of C less than 30. And so this is a very basic universal consistency constraint on CFTs that have non-diagonal fields and degenerate fields. And this constraint, I think, explains why it's hard to find solvable CFTs at large central charge, meaning a central charge close to plus infinity. And that's a problem for, well, applying these CFTs to quantum gravity in particular. So, any questions on that? If not,
I guess maybe just this is one comment. We wouldn't really expect in a large single charge to have this degenerate field anyway, because it wouldn't be unique for large. For C greater than 1 in a unitary theory, you cannot have V1, 2.
right, but the point is that it can belong to the extended spectrum, so you don't really care about unitarity. For example, this degenerate field is present in Liouville theory, and Liouville theory exists also at large central charge. So what saves Liouville theory is that it's diagonal, so you don't have this particular problem. Okay, so let's start building actual conformal field theories. And the first one is a generalized minimal model. Well, why I'm starting with something which is generalized instead of original thing? Well, it's because generalized minimal models are actually much simpler than minimal models. But they happen to be constructed later because, well, first, they are non-rational, so infinitely many primary fields. And second, well, their torus partition function does not exist. So when people were looking at modular invariant torus partition functions, they didn't find them. But to construct them, you only have to assume that the spectrum is made of all diagonal degenerate fields. And basically, that's it. I mean, you have your CFT. You know that these fields are closed under P's, so this obeys our basic constraint. So the second basic constraint here, well, is in fact not true for the whole spectrum, but you don't really care because in any OP you have finitely many terms. So, well, let me rewrite. So the OPs here, it's VV_R1 S1, VV_R2 S2 equals sum for R from R1 minus R2 plus 1, R1 plus R2 minus 1, F from S1 minus S2 plus 1, S1 plus S2 minus 1. This sums run by increments of 2, VRS. So any OP is in fact a sum of finitely many terms. So, well, plus dissonance, of course, but so you don't have to worry about convergence.
Okay, structure constants.
So here I'm in the process of sketching all these CFTs, so structure constants are for a later lecture. So indeed, then you have to work out structure constants.
Is the claim that they are unique? If it assumes it's a spectrum?
Right. The claim is they are unique, and we can, in fact, compute them. But this lecture is about sketching basically all the CFTs that plausibly exist.
You could also put some multiplicity, right? This is a very famous spectrum where for each R and S you only have one.
Right. Well, I suspect that this would boil down to the same thing or to several copies of the same thing because you see, precisely the structure constants are unique. So even if you want to add multiplicity, you'll end up to have the same correlation functions independent of the multiplicity. Well, yeah, that's a bit quick. It would maybe deserve more study if someone is motivated. But not just in generalized minimal models, in fact. Okay, so after this quick and easy victory, let's construct Liouville theory. And for that, we'll start with the generalized minimal model and assume the beta squared is real, positive, and non-rational. And okay, why am I doing this particular assumption? Well, you'll understand if you look at the values of the momentum here for the field for all these degenerate fields. So the momentum here is PRS with R and S integers. So now with this assumption, I can assume beta is real. And even positive if I want. And if you look at these momentums, well, they all fall on some line, on the real line. So I'm in the complex P plane, but this is the real line. And here I have the vector beta, and here the vector beta minus 1. So beta minus 1 goes in the same direction as beta. That's the assumption here that beta squared is positive. And if you look at all these values PRS, now I have this crucial minus sign, and therefore I'm claiming these values are dense in the real line. So in mathematical terms, I'm claiming the closure of the set of PRS is the whole real line. So I want to use this to construct diagonal fields here by taking limits of my degenerate fields and sending Rs to infinity such that PRS go to some P here, which can be any real number. So if I do that, the null vector here, which is at level Rs, will go to level infinity, so basically it disappears. And I'm getting a diagonal field, which is no longer degenerate. So with this limit, the claim is that the limit of the spectrum, well, it gives me just the spectrum Vp for real P. So let me put a 1/2 here because of the redundance between P and minus P. That would be the spectrum of Liouville theory, which for the moment has a central charge less than 1 because of this restriction. Well, in fact, it's not all values less than 1 because I also assume beta squared to be non-rational, but then I can take a limit in beta squared and at least I can get all central charges less than 1. So all real positive beta squared. Okay, so if we accept that generalized minimal models exist, so basically we get that this Liouville theory must exist as well as a limit. So what is its operator product expansion? So we take Q1, Q2, and then we have to take the limit of this operator product expansion. And well, all the indices basically go to infinity. So if you look at it, you see that here you get any momentums, essentially.
So we used to have 7 possible families of the degenerate fields in the general CFT. Now we only have one generalized minimum. Per family of.
Right, so we could try to construct other CFTs with fewer degenerate fields. So here I'm assuming we have all degenerate fields for the moment.
Okay, but we could in principle imagine a generalized minimum model with just a DRS for R odd, R even, and S any integer.
Yeah, right. We could do that, and if you do that, well, it's a submodel if you want. So it's all included in the generalized minimal model.
Sorry, what is the 1/2 there?
So 1/2 is because Vp is the same as V minus P. So when I'm writing all real numbers, it's redundant.
Okay.
Okay, so now I'm taking the OPE by taking a limit of this OPE, and well, it becomes continuous, it becomes an integral, so I have the same 1/2, by the way, and naively, I get this. Well, I say naively, which means I don't really get this. So why don't I really get this? Well, the problem is that, okay, that's fine as far as primary fields are concerned, but you must remember that it all comes with descendants. So some of the descendants, and then these descendants come with coefficients. So I have some coefficient f delta L, delta 1, delta 2, and then this LVP, let's say. And this coefficient, if you remember, it has poles. It has poles when the conformal dimension delta here becomes degenerate. But now, precisely the real line here over which I'm integrating is exactly where the degenerate fields live. I mean, that's how we got this Liouville theory in the first place, by taking a limit from degenerate fields, which live all over this line, which are dense in this line. And that's how we constructed our diagonal fields. And so, in principle, I have this dense set of simple poles in this coefficient, in this integral. And the trick then is that when I'm computing this OPE, I should actually shift the integration line. So VP1, VP2 is in fact 1/2 R plus I epsilon VP. So the integration line will be this one now, and it will avoid all the singularities. So, but now to do that, I have to assume that I have some VP with complex values of the momentum, which, if you want, I'm assuming by saying this is an extended spectrum. So the extended spectrum of this Liouville theory would include all the VPs with complex momentum.
Can you in principle derive this contour prescription with the plus I epsilon by carefully taking the limit of the generalized minimal model OPE?
Yeah, so that would be nice indeed to, but I've not tried. I don't know if it's possible. The way we derived this prescription was by guessing, basically. So we guessed and then we checked crossing symmetry numerically. So that was work with around Santa Chiara in 2015.
So minus I epsilon would blow up.
No, minus I epsilon would give you the same result due to the symmetry between P and minus P.
Also, naively, it would, well, maybe you will see it in the descendants, but if you look just at the primaries, you have the feeling that, in fact, the OP of VP1 and VP2 doesn't depend on P1 and P2.
No, but here is a very schematic notation, but you have, well, first of all, you have a structure constant here, CP, P1, P2, right? Yeah, and then you have the dependency as well. Okay, so we have Liouville theory with C less than 1, but what about Liouville theory with a more general value of C? I mean, after all, originally Liouville theory was constructed from path integral for C bigger than 25, and then it can be continued analytically to C complex, essentially. Well, except in fact this line, minus infinity 1. So now we are starting from the opposite direction. We are starting from C less than 1. Can we recover, by analytic continuation in C, can we recover the Liouville theory for more general central charge? And well, we could try at least, but in fact this would fail. And the reason is, again, these poles here. So these poles here, they sit on this line. These poles which appear in this OPE, they sit on the line, but that's true only for C less than 1. As soon as C leaves this half line, what happens is that the pole, they start to form two wedges here. So they are like this on some lattice. And then there is an upper lattice as well. So suddenly you have poles which jump off the line, and then they start to go until infinity, in fact. I mean, these are infinite wedges. So whatever you do, you cannot put this line far enough. It will always get crossed by infinitely many poles. And this prevents you from continuing analytically from C less than 1. So there is no analytic continuation. And therefore, if I want to define Liouville theory for general values of the central charge, all I can do for the moment is to assume it exists. So I'm defining basically spectrum to be, well, the same spectrum, 1/2 of the set of VP for real P. And I'm assuming the OPE to be, well, VP1, VP2 equals 1/2 integral VP. where now the integral is really over only real momentums because the poles have moved off in the complex plane, so I don't need to shift the contour anymore. I don't have any more poles on my integration map. But nevertheless, I could still define an extended spectrum. In fact, I could define the extended spectrum of Liouville to contain all complex momentums. So that still works by analytic continuation in P. I could even add in the spectrum all the degenerate fields if I want, which would in fact make the generalized minimal model a subsector of Liouville theory. So all this is a big extended CFT if you want.
What's the right hand side of the OPE if you do OP of something which is not in the real line?
Right, okay, so if I'm moving too far off in the complex plane for this P1 and P2, this OP will start having discrete terms in addition to the integral. So you have to derive it by analytic continuation. Okay, so this is enough for Liouville theory, and probably that's a good moment to make a pause before defining more complicated things like minimal models. On voit une délégation, on va peut-être attendre le retour de la délégation. Okay, so let's start again with an A-series minimal model. So A-series, which in other words means diagonal minimal model. So the idea is to look for rational CFT. So rational means having finitely many primary fields. So now let me make another assumption, which I hope you'll find plausible. It is that a rational diagonal CFT on the sphere is equivalent to a finite set of degenerate representation which is closed on the fusion.
The definition of rational is that it has a finite number of primaries.
Yes.
And can we show that this implies that the primaries have rational conformal dimensions?
Okay, there are arguments, but I'm not sure they are so general. They probably would anyway require modular invariance. So I think here I'm focusing on the sphere. So probably you can't show that they have rational dimensions.
Using modular invariance.
Yeah, but now we derive it by assuming we get only degenerate fields, basically.
And vice versa, like can you say if you assume that you only have representations with rational dimensions, can you show that then you must have a finite number of primaries?
No, you cannot show that because it's wrong.
Ah, okay. And what's the counterexample?
Well, you take any model like, well, loop model at rational central charge, for example. All the dimensions are rational.
And it has an infinite number of primaries.
Yeah.
Okay. Maybe then what similarity?
Maybe. But minimal models are not unitary in general. Okay, so let's accept this claim and look for some set of degenerate fields which is finite but closed under fusion. So we know already that if we start with V12, in general we generate infinitely many fields. So that's a bad start. But that's because we were doing it at generic central charge. So now, if it's rational central charge, we can have multiply, well, fully degenerate fields with several null vectors which vanish, and that will give us more constraints. So the claim now is that we need to take theta squared rational and to look at fully degenerate fields. So there are two cases, either it's positive or negative. So let me start with the case of beta squared negative, which means, well, the central charge is more than 25. Then let's look at the simplest fully degenerate field we can have, which is VF1 Q plus 1. It's fully degenerate because it has a null vector here at level Q plus 1, but also a null vector at level P plus 1. So then if we start to fuse this field with itself, we get finitely or infinitely many fields. Well, that's an exercise you can do using these fusion rules, basically. In particular, you can show that this field, let me call it V, so V times V gives you V11, which is only simply degenerate, plus V2 P plus 1, 1. And, well, actually, if you do it again, you'll see that the first index, I mean, nothing bounds it. You can still get infinitely many fields. So, although it's not a theorem, I think it's the general situation for beta squared negative. You can't get a finite set of degenerate fields that closes on the fusion. So I'm going to focus on the other case of beta positive, which means C less than 1. So here we really want to start with V12 and V21 and see what we get by repeated fusion. And so V1 and 2. So the claim is that we get the cat stable. So first I'll make the claim and then I'll argue that it's true, or even prove it. So what is the cat stable? It's the set of R and S which belong to, so let me call it KQ. So now beta squared is Q over P, with P and Q positive integers, co-prime as well. So let me define the cat stable as just 0P times 0Q intersection N times N. Which means, in fact, the following. So in the RS plane, I'm starting with 1 and stopping at P minus 1. Here I'm starting at 1 and stopping at Q minus 1. So the cat stable is the set of all these points with integral coordinates. And the nice thing is first that if you are in the cat stable, it means you're multiply degenerate. Well, I'm assuming you are from my field. I hope you don't mind. So the term VF, so I'm calling it F like fully degenerate because VFRS is VFP minus 1 Q minus S. So it has two, well, in fact, it has infinitely many vanishing null vectors. Okay, so I have to compute the OPs of fields of this type. And to do that, I mean, it will be deduced from the general OP, which is here. So, well, first, in fact, we have to, the set of fields we can obtain is a subset of this set here, because we have to obey the constraints from having null vectors here at level R1 S1 and here at level R2 S2. So therefore, VF R1 S1 VF R2 S2 is included in this sum here, starting from R1 minus R2 S1. But then, I mean, by assumption, my degenerate field here, oops, I mean, this expression, well, let me rewrite it here. I have V Rs equals V P minus R Q minus S. So it also has an extra null vector at this level, P minus R times Q minus S. And this means that the OPE, the same OPE, also has to be included in what I would get by replacing R1 by P minus R1, R2 by P minus R2, etc. So that's the sum, R1 minus R2 plus 1, and then 2P minus R1 minus R2 minus 1. So here I'm just doing R1 P minus R1, R2 P minus R2, and the same for S. With Q here. So sum S equals S1 minus S2 S1, and 2Q minus R S1 minus S2 minus 1 VF S. Okay, so now I have basically to take the intersection of these two sets of degenerate fields, but okay, I have to take the intersection modulo this identification. I mean, I could have fields in principle which are equal here, although they have in fact different indices. But this in fact does not happen, because if P and Q are coprime, one of them must be odd. Let's say P is odd. And here, if you look at the first index R, and the first index here, they are all, modulo 2, they are all equal to the same number. But if you do a P minus R, you change the parity of that index. So basically, you can't have this field equals this field except if they have the same indices exactly. They cannot be reflected on one another. Therefore, in fact, the OP you get by taking the intersection is just, well, the sum here are up to the mean of these two numbers, which is, well, mean R1 plus R2, 2P minus R1 minus R2, minus 1. There is the sum of over the S index, which is similar, VFR. Okay, so now the nice thing of having a mean here is that now we see that you get only fields in the CATS table if you started inside the CATS table, if our two fields are in the CATS table, because, well, this R now runs until this number, but this number has to be at most P. So the CATS table itself is stable under fusion. That's the first conclusion. Then I should show that these fields are in fact fully degenerate. So by taking a product of two fully degenerate fields, I also get a fully degenerate field. And that's an exercise which I think we can probably skip. Give you a hint. So if you remember, we detect degenerate fields because their OPE with some generic field is finite. Well, a finite number of primary fields appear here. And so the claim is that now VF RS with RS in the CATS table times VP, the result is 0. So that's what you should show based on the fusion rules of this field, which you can compute by, again, taking the intersection of the fusion rules for indices R and S with the fusion rules for indices P minus R, Q minus S. You will find nothing is left. And then if you know that, then of course, if you take a product of fully degenerate fields, well, you have to find, by associativity of the OP, you have to find more fully degenerate fields. So this allows us to define the A-series minimal model. So let's call it AMMPQ by its spectrum, which is when the set of fields in the cat table fully degenerate with RS belonging to the cat table. But here I have the 1/2, which due to this ambiguity here of reflection. And now I just have to specify which values of P and Q are allowed. Well, let me remind you, it was P and Q positive integers, P and Q co-prime. And well, we can achieve P less than Q by symmetry between P and Q. So we know the spectrum and we know the fusion rules here. Okay. So other questions on this minimal model? Well, if not, let's do what we now usually do when we build a new CFT, meaning taking limits to try to build even more CFTs. So what limits could we take? Well, these values of P and Q, well, let me remind you, beta squared is Q over P. So we have basically almost any rational number here. So this beta squared, we can take a non-rational limit. So the first question is what happens when beta squared goes to, well, let's say when Q over P goes to some beta 0 squared, which does not necessarily belong to Q. And then it really depends when you take the limit, because you should specify what you do with the indices R and S now. So if R and S are fixed, what happens? Well, it means you are taking some fully degenerate field, VRS, and you want to take its limit, well, just the limit in the central charge. So beta squared goes to beta 0 squared. So your fully degenerate field sits somewhere in the cat table. And then the cat table, when Q and P go to infinity, so the cat table starts to become infinite. Your field does not care about that. But what happens is that it has a null vector table RS, which still exists in the limit, but then it has the other null vector, which was at level P minus R, Q minus S, which goes to infinity, and so it disappears. So of course, you're in a degenerate field now, with only a null vector at level S. Since at generic central charge, you don't have multiply degenerate fields. So if you take the limit of the full model by this, this limit, so Q over P goes to beta 0 squared and R and S go to fixed, sorry. Well, what do you find?
Generalized normal model.
You find the generalized minimal model, so you find the whose spectrum is made of all the degenerate fields, because now your cat table, it has become infinite. The boundaries have gone to infinity, so you're left with all possible indices R and S, all possible integers.
The only way to do this, so unitary minimal models have P equals Q plus 1.
Right.
So basically the only irrational point that you can approximate with the unitary ones is beta squared equal to 1.
Yes, right. Yeah, but you can do that even for a rational beta 0 squared, in fact. You don't have to assume it's non-rational.
But if you do this for like beta squared equals 1, do you approach a rational CFT, or what do you approach?
No, you still approach, I would say, generalized minimal model at central charge 1, which I'm not fully sure exists, so I'm not sure it has been really studied. Yeah, one has to check if there are not any subtleties. Okay, so Now that was easy, so that was, but now let's do limits where R and S are not fixed. So one reason to do that is that, well, if beta squared now is no longer rational, then PRS, we know it can go to any value basically when R and S go to infinity. We can send it to some fixed number, so we could get in principle any diagonal field. So the limit now of this PSRS when, well, PRS go to some P, we still P go to beta 0 squared, well, gives us a generic diagonal field, and therefore I would expect the limit of our A series minimal model to be Liouville theory with well, C less than 1. Well, to do that, I have to check that in fact I get the correct operator product expansion. But if you look at the operator product expansion, you'll find basically all of these fields with real momentums appear in the OP when you take the limit. So you also recover the correct OPs.
Are the structure constants known for the HTML model for the
Right, yeah, they are known.
and you can take a limit and get the DOZZ formula out of it.
Well, it's not DOZZ because it's C less than 1, so it's a different formula, but yes, you can get it. Yeah, that works at level of 3-point functions, yes.
Is the formula that's like 1 over DOZZ?
To some extent, yes.
Yeah, okay.
Okay, so now there is a big subtlety, which is that in fact you don't have to get Liouville theory because you can fine-tune the parameters and get something else, provided the beta 0 squared itself is rational. So let me quickly explain that. So in the case beta 0 squared is Q0 over P0, then what you could do is to first you could fine-tune P and Q by assuming QP0 minus PQ0 equals 1. Right? So that's really a lot of fine-tuning because if you want Q over P to have the correct limit, all you have to do is to take QP0 minus PQ0, well, much less than P, as P and Q go to infinity. But now you don't just assume they are much less than P, you don't assume they are square root of the square root of P, you really assume they are fixed to 1. So that's a lot of fine-tuning already. But it's the same you wanted to do with your unitary minimal models, in fact. And in addition, I want to fine-tune R and S as well. So to motivate that, let me write PRS when we take this limit with P and Q fine-tuned like that. So PRS are following. I can write it as square root 1 over square root 2P 1 over 2 square root P0 Q0 times RQ0 minus SP0 plus the 1/2 R over P plus S over Q plus something of order P minus Q. So here I'm taking the formula for PRS. So you see originally PRS is just 1/2 square root Q over PR minus the square root P over QS. And I'm taking P and Q. I'm expanding P and Q near their limit values P0 over Q0. I'm expanding Q over P equals Q0 over P0 plus something of order 1 over P. So this is the result of this expansion of PRS. So if I do that, now let me do my fine tuning of R this. So let me assume that R Q0 minus X0 is fixed. And let me assume also that R over P and S over Q both have finite limits, and it's the same limit X. So if I do that, the limit of PRS, so this is, let me call that N. If I do that, PRS in the limit is this N plus X. Well, X is the number between 0 and 1. N, by definition, is an integer. Well, not necessarily positive. So it looks like I have reconstructed any real number here in a very special and fine-tuned way. But the thing is, if you do this special limit in the fusion rules, well, you won't find the trivial fusion rules of Liouville theory, which were Vp1, Vp2 equals 1/2 integral Vp. No, here you're starting from the fusion rules of minimal models. So that was VR1, S1, VR2, S2 equals some, well, there was a mean there. Mean R1 plus R2, 2P minus R1 minus R3 minus 1. So you start from these fusion rules, and you do this type of limit, and the claim is that you find the fusion rule Vp1, Vp2 equals, so you, well, sorry, it starts with a sum for n, n1 plus n2, p0 plus q0 plus 2v, and then you have an integral over x1 minus x2 to the 2 minus x1 plus x2, and then you have vnx, which is the limit VRS is some vnx. So basically, if you do it carefully, this non-trivial bounds in this sum here will give rise to non-trivial bounds in this integral from x1 minus x2 to 2 minus x1 plus x2. And therefore, you don't get an integral over all possible momentums on the right, you get only part of them. And so you get a CFT which is not Liouville theory because it has non-trivial fusion rules.
This is known this year.
Yeah, it's more or less known. Not very well known, but it's known. So let me give its name at least. I would call it a Runkel-Watts type CFT. Because Runkel and Watts in 2001 found the first example, which was at c equals 1, by taking limits of unitary minimal models. But their construction works because their beta squared was rational. But the similar construction works for any rational beta squared. So this type of CFT, so now let me look at the complex C-plane. So we take a limit of minimal models. The central charge goes to some rational limit, C0. We get this non-trivial Runkel-Watts type CFT. Now, there is another way to get it, which would be from Liouville theory at complex central charge. And again, you have to fine-tune the limit a bit to get there, but it can be done. But
only rationals, but less than 1.
yes. Now, this claim can look a bit paradoxical because Liouville theory has trivial fusion rules, right? I mean, which I wrote again somewhere. I mean, in Liouville theory, VP1, VP2 gives you all an integral of all possible momentums, but here I'm claiming that in the limit, I only get a subset of that. So how can this be? Well, the point is that in the limit, it's the structure constant here, which appears in the OP, which has zeros. So you reconstruct these fusion rules by looking at whether the Liouville structure constant goes to 0 or not. So in the limit, if you want, as a function of P, the Liouville structure constant, Cp P1, P2, will have things behavior like that. It's some nice function, smooth function, and then suddenly it falls to 0 in some interval, and then it starts again and falls to 0 in some other interval. And these intervals correspond to the places where the momentums which don't appear in this OP.
And so this function, these OP coefficients, are also some like analytic continuation of the DOCC, basically.
Yes, basically yes. So you can get them either from Liouville with C less than 1 or from DOCC.
And so the DOCC formula has this like non-analytic behavior in this for C less than 1.
Yeah, right. So the DOCC formula in principle does not have any limit when C goes to this half line. But if you take a limit in a special way, and if your target is rational, then it can have this limit, but it's no longer smooth. It's no longer continuous.
How can the fusion rules of the Ruckel-Watts that you wrote there, the BP1, BP2 equals this sum?
Yes.
So if the spectrum is continuous, the BP1 and P2 are continuous, how can you have a discrete fusion rule?
No, it's not really discrete. I mean, here we have this integral. What is discrete is only the value of n of the integer part of this momentum here. So the momentum you get for this nx is just this expression with n the integer part and x the fractional part.
Okay, there's a sum and an integral.
Yeah, there is a sum of an integral.
There is a plus between the sum and the
No, it's a sum of integral. The sum is over n and the integral is over x.
And there's two, and those two numbers are the bounds of the integral.
Yeah, right. x1 minus x2 and 2 minus x1 plus x2.
So the field has momentum n1 plus x.
Well, it has this momentum here, but now I'm labeling it by n and x instead of labeling it by its momentum. Yeah, sorry, that was maybe a bit quick. Yeah, you'll have more details in the notes about that.
In x, so what values does, x is in 0, 1, but it's never 0, because it's an open interval.
If you want, so you see that these bounds, in fact, prevent it from reaching 0, because the lower bound is, well, modulus, absolute value of x1 minus x2, well, except if x1 is x2, in fact.
I'm just wondering if you choose this Vx to be 0, if you can have also a small
The discrete part.
this fusion rule would have some discrete part where the x is 0 and you have sum over n, and then a continued part for x different than 0. But maybe it's not possible.
No, I don't think so. Okay, but let's move on, because I mean, this is very nice, I think, CFT, but also not the most important one. It exists as rational central charge. It's a bit special. So I'd like to move on to non-diagonal CFT now.
Sorry, one last question. So these Ruckel-Watts CFTs, do they have any like statistical physics application?
Well, not as far as I know. non-diagonal CFTs, now I'm still keeping two degenerate fields. So the first one is D-series minimal models. So we want to build rational non-diagonal CFT. And our basic assumption is that we use the same representations as we did in A-series minimal model. So we start with the cat table. So indices in the cat table. So, and we want the left dimension to be the cat table, the right dimension to also be in the cat table. Which means if we write our non-diagonal field as VRS, in fact we want delta RS to be equal to some delta, let's say R1S1, which with R1S1 in the cat table. Well, it doesn't necessarily mean that R and S belong to the cat table because we have identities. In particular, we have this identity delta RS equals delta R plus P over 2 S plus Q over 2. Okay. So the cat table is nice, but it has a big problem for us, which is not invariant under the reflection of S goes to minus S. So our non-diagonal fields, if you remember, they have on the left delta RS and on the right delta R minus S. And so if RS is in the cat table, R minus S is not in the cat table. But I have to use this now this identity to rectify this situation. So the idea is that we can take RS in a shifted cat table. Let's say when we look at the center of the cat table, which is at P over 2, Q over 2. And that's where we start to measure our R and S. If we measure from here, the cat table becomes invariant under S goes to minus. So what this means concretely is that we take RS to belong to the following set. So minus P over 2, P over 2 intersection Z plus P over 2 times minus Q over 2, Q over 2 intersection Z plus Q over 2. So that's the basic ansatz. And if I do that, both the left and right dimensions coincide with dimensions from the cat table. So now I have to check that the spin is still integer. So what is the spin? Well, the point is that R is P over 2 modulo integers, and S is Q over 2 modulo integers. So P and Q are co-prime integers. So if both of them are odd, then I'm cooked because RS will be typically 1/4 or something. So I have to take one of them to be even. I can't take both of them to be even, otherwise they would not be co-prime. So let's take, by convention, P to be even. Right? And Q, therefore, has to be odd. And then the integer spin condition, it's still RS belongs to Z. Now Q being odd, it implies 2R. No, sorry, R must be an even number. And S, of course, will belong to 1/2 plus Z.
Before that minus RS was a half integer, isn't it? In the days, no, it was an integer, not a half integer.
Well, to be half integer indeed is a constraint from the existence of degenerate. Well, I cannot have both of them to be half integer, otherwise at some point their product will be not even half integer. Sorry.
And is there overarching maybe logic of this part? So you can actually derive like the ADE classification of minimal models purely from representation theory without using like modular invariance?
Yeah, it's a good question, and in fact, I'm still struggling with the E series. So I don't have at the moment a good argument for the E series. So we'll have to do with the A and D series.
And then one would have to prove that this is all there is.
Well, probably this is not all there is because we're on the sphere. So if we're relaxing the constraint of existence on the torus, so we can probably get more.
More minimal models.
Yeah, possibly. I'm not sure if there are more non-trivial possibilities. I mean, you always have the possibility that we mentioned of taking a subsector of a minimal model, so that's easy. But I'm not sure if you have a really interesting non-trivial possibility.
So yeah, I'm thinking of just minimal model, not like generalized. Like just take the representations of the catch table, and show that the only possible spectra that you can have consistent are ADE.
Right. So that looks indeed plausible, but you would have to do something about the E series. Okay, so we have found the values of we have found basically our non-diagonal spectrum now. So we can start our DMM minimal model spectrum with the non-diagonal sector, which is one half of VRF non-diagonal field for well, R belongs to 2Z, S belongs to Z plus 1/2, and of course R between P over 2 and minus P over 2, and S between Q over 2 minus Q over 2. Now, if you remember, we had also concluded that in the presence of degenerate fields, by doing fusion, these numbers are less mostly conserved modulo integers. And this rule was derived from the monodromies of fields. So of course, the monodromies of diagonal fields are trivial because the monodromies, when we computed them from spins, but diagonal fields don't have spins. So for the purpose of these rules, diagonal fields, they count as having R and S equals 0. So in D-series minimal models, well, you have non-diagonal fields which have S half integer and diagonal fields which have S equals 0. And therefore, the conservation of S modulo Z boils down to the conservation of diagonality. Meaning, if you take a diagonal times diagonal, you have to find diagonal. Diagonal times non-diagonal equals non-diagonal. And non-diagonal times non-diagonal goes back to diagonal. So that's what I would call conservation of diagonality. So
what does it mean that a field is diagonal, that S is 0? Or?
Right. Diagonal field for me, in this context, is just a field. Well, one of the fields of the A series minimal model, if you want. So a field in the Katz table with the same left and right dimensions. But for the moment, I did not say which of these fields belong to this model. In fact, I want to construct the diagonal sector from the non-diagonal sector. So here we have a very plausible answer for the non-diagonal sector, and then let's get the diagonal sector by just fusing these fields among themselves. And I know that by fusing non-diagonal fields, I should get only diagonal fields because of this conservation of this. Okay, so in fact, it's quite easy to see what we get by doing that. We know the fusion rules. I mean, these fields, although I wrote them in a funny notation with non-integer indices, but they still obey my fusion rules, my general fusion rules of degenerate fields. I mean, this type of fusion rules, right? So in principle, I can derive what I get by fusing them. And I could expect that I get all the cat stable, but I don't, because there is this constraint that the first index is even, and after fusion, it will make the first index odd. And so therefore, what we get is in fact 1/2 of the cat stable. So, so this 1/2 is due to reflection symmetry, but we'll get an extra constraint as well. So that's a degenerate field, RS, with RS in the cat stable, KQ, and in addition, R odd. And that's the full spectrum of a D-series minimal model. And then, well, I have to write the fusion rules.
These spins here as deep, they spin 0, but they have like RS on both left and right, if I remember.
Yeah, right. In fact, they are fully degenerate. So these are really the same as in the A-series minimal model, except that I'm having this extra condition. R is odd. Well, in fact, we could relax a bit because here we have assumed the spin to be integer, but we could take an extended spectrum with a non-integer spin. So the extended spectrum, well, let me say it's red. So in the extended spectrum, you can take R to be just integer instead of having it even, and the S here. Well, you wouldn't have this condition anymore in the extended spectrum. And then you get an extended model where the spins are half integer. So this is called the fermionic minimal model. I mean, fermionic minimal models were recently studied by Runkel and Watt, again there.
It's because it's a recent thing, but do we have a classification of fermionic minimal model? Or not yet? Is there like an IDE classification of fermionic minimal model?
Okay, I'm not sure. It's a 2020 paper, and I'm not sure there is a classification. I would have to check.
You have some kind of concrete realization.
Well, I'm not sure what you mean by concrete realization. I don't think they have a lattice model. I think their approach is basically axiomatic, but maybe a bit more formal than my approach. So it's based on categories. But I mean, it's a good way to derive this type of models.
Non-diagonal fields, they are not fully degenerate.
So the non-diagonal fields, they are fully degenerate, both on the left and on the right, which I admit is not manifest in my notation. Okay. So let me write it here. There is a F, but so let's write the fusion rules of this D-series minimal model. So in principle, it's just more or less the same as in A-series, but since I have changed notation now with this indices R and S, which are not even integer anymore, I have to slightly modify the fusion rules. Well, let me write explicitly the fusion rules of two non-diagonal fields. So this is a sum from R equals R1 minus R2 plus 1 to, to P minus R1 plus R2 minus 1, sum from S equals S1 plus minus S2 plus 1 to Q minus S1 plus S2 minus 1 of GF RS. So now the upper bound is a bit different because this R1 and R2, they are no longer in the cat table, but they are in this shifted cat table. So they obey R less than P over 2 in particular. So this number is still, this upper bound is still positive.
It would shrink to the empty. If you put the two together, the upper and the lower bound, it could be empty, isn't it?
No, I don't think it gets empty. It reduces to just one field.
Okay.
Okay. So what do we do when we build a new CFT? We take limits, of course. So what limits can we take of these non-diagonal minimal models? Well, we can take, of course, the central charge, or the beta squared, which is originally Q over P, to some arbitrary value. Let's say a non-rational value, a priori, beta 0 squared. And what happens if we do that? Well, we first have to look at the spectrum. And starting with degenerate fields. With non-diagonal fields here. So the simplest thing to do, of course, is to keep R less fixed. In fact, that's the only thing we will do. I mean, I'm not sure you can do something different here because I mean, you still have whatever you do to R less, you still have to keep the spin half integer, the limit. So I think you basically have to keep R less fixed. So what is the limit of the spectrum now of this series minimal model? Well, for the non-diagonal sector, it's quite easy. What happens is that now the bounds of my cat table again go very far away. So the bounds are P over 2 minus Q over 2 minus Q over 2. They go to the infinity. So R less, well, they just belong to this lattice 2z is equal to 1/2. So P R less, R is even, and S is half integer. And now we have to say what happens to the diagonal sector. And a priori, it's not trivial to say because, as we saw in the case of A-series minimal models, you have several different ways of taking the limit of the diagonal sector. You can fix R less, or maybe you can send the momentum to some arbitrary value. That you could also do in this model in principle. So to know what to do, we have to, in fact, look at the fusion, because the way we constructed this series minimal model was to get the diagonal sector from the non-diagonal sector by fusion. So what happens in this fusion rule now? If I take this limit, so I'm keeping R1, S1, R2, S2 fixed, I mean, because I'm keeping indices fixed in the non-diagonal sector, and I'm sending P and Q to infinity. So in the limit, it seems I'm just getting rid of the upper bounds, and it seems I get this discrete spectrum. Okay, so that's the naive limit. So is that really what happens? So, okay, it would be a test of how awake you still are if I didn't give too many hints of the answer by calling it naive and asking if this is really what happens. So the question is rather what's wrong with this result?
I was a bit distracted. Sorry, those fields are the diagonal ones or something?
Okay,
Right.
so here I'm starting from this diagonal fully degenerate fields. So they remain diagonal, of course, in the limit. Well, they're only simply degenerating the limit, of course. One null vector goes to infinity. But then, what's wrong with this?
Generalized minimal models.
Yeah, it looks like, but in a generalized minimal model, you would have a finite sum. Here, you seem to get an infinite sum. Yeah, so that's a good remark. And what's wrong with having an infinite sum? Well,
It's a bounded from
the dimension is still bounded from below, but nevertheless, this sum diverges. And it's divergent because, well, if you look at the momentum here, PRS, well, it's almost the same as the spectrum of a generalized minimal model. So therefore, the PRS are again dense in the real line. And the fact they are dense means if you look at some interval, some small interval of momentum here, so let's say in the P line, you look at some small interval, and if you do these sums, you will get infinitely many values in this small interval. And therefore, if you do an OP, it has to diverge.
Could be illustration nonsense.
No, but the point is that essentially, I'm anticipating a bit, but the structure constants are entirely determined essentially by the conformal dimensions. So if the momentum is in some small interval, it means the structure constants don't change a lot because they are in fact analytic in their momentum.
There's something I think Liouville theory, we had a continuous spectrum, and we had by definition a dense set of operators on the right side.
Right. So,
we had a problem with this. So what's different here?
Well, in fact, that's the solution. What we want is to have an integral. This sum is divergent, but the integral would be convergent as in Liouville theory. So what we will do is to take the limit slightly differently. So instead of naively taking the limit of V R1 S1 V R2 S2, all we have to do is to take the limit of, let's say, 1 over Q VR1 S1, VR2 S2. So we divide this infinite result by a factor of Q. And if you do that, well, you still find a version of this sum, but this sum is over, in fact, values that are dense in this line. So essentially, you get an integral. Yeah. So the regularization of this infinite sum is just an integral, which is finite.
And does it mean you should put the 1 over Q both on the left-hand side and 1 on the right-hand side? Because
of which equation?
The last equation.
This one?
Yes.
No.
What you are saying is that in fact 1 over Q times VRS has a finite limit.
Yeah. I'm saying, yeah, what is written?
No, but I think you say more. Because VP isn't part of it. Well, if you divide, what are the fields in the limit? What I'm saying is that if you put one more Q on the left and one more on one on the right, then this is okay.
No, but on the right, I don't have Q anymore. I have taken the limit. Q is not a parameter.
Limit 1 over Q VP. This equation is inconsistent, is it?
Okay, so VP is, yeah, okay. Indeed, maybe I should specify what is VP. For me, VP is something finite, but the question is, how do I get VP as a limit of FRS, right? So probably I should do something here, but I'm not sure I have to do much because, I mean, in the limit R and S go to, well, PRS go to P. So this is perfectly fine. Okay, maybe we can discuss after the lecture.
This is for the D series that you.
Well, here I'm taking a limit, a non-rational limit of the D series. So,
what is the difference now between the A series? I mean, you can do.
well, the D series has a non-diagonal sector, which is made if you it's made of these VRS, which are non-diagonal, which have delta S on the right and delta R minus S on the left, or vice versa.
When you go to the limit, you still find
Right.
diagonal.
So let me rewrite the spectrum I get in the limit of the D series minimal model. So that's when Q over P goes to some beta squared. So the non-diagonal sector which was written here was just VRS. And now the diagonal sector is just a continuum of fields with arbitrary real momentums. So that I would call a generalized D-series minimal model.
Kind of Liouville extended with.
Yeah, it looks like an extension of Liouville theory because it includes the spectrum of Liouville theory. However, there is a subtlety, which is that it does not have the same structure constants as Liouville theory. But we can see that only when we study the three-point functions in more detail. So it's not an extension of Liouville theory. However, like Liouville theory, it probably has an analytic continuation to more general central charges, because for the moment the central charge is p less than 1, but probably the model exists for any central charge which obeys our condition on for non-diagonal CFTs, so real part less than 13. Well, in the case of Liouville theory, this is not really an analytic continuation. As I explained, there is no analytic continuation, but still we assume Liouville theory exists in the complex plane. In the case of this generalized D-series minimal model, it's probably, at least for some correlation functions, it is an analytic continuation. Maybe not for all structure constants, maybe not for all correlation functions. Okay, but that's all we can say now about this CFT, and I think we stop for today. And next time we'll be ready to talk about CFTs with just one degenerate field, namely loop models.
Question. So, is there anything special that happens if we take the limit of beta going to 0? For example, by, let's say, take Q fixed and P going to infinity.
Well, I think a priori you don't get a CFT anymore because the central charge becomes infinite.
Yeah, minus infinity.
Yes. So if you keep the conformal dimensions fixed in general and send the central charge to infinity, what you do is you destroy the Virasoro algebra, but you still keep the global conformal symmetry. You could get a global CFT, but it depends on how you take the limit.
And the great reason why I'm asking about this limit is that when you do minimal strings, there's this evidence or it's believed that if you take the 2, p minimal string and you take p to infinity, then this is equivalent to this two-dimensional theory of gravity called JT gravity. And so I was wondering from the CFT point of view how to define this limit and if there is a CFT there.
Yeah, no, that's a good question. But I think to answer it, one has to look in more detail at correlation functions and find a way to take the limit for, in particular, the limit of these indices Rs in the minimal model, such that correlation functions have a finite limit.
In principle, I think the claim is that they do. Like, for example, right? Like if you do it, if you do this limit, maybe not in this way, but like starting with Liouville theory, with then the correlation functions, I think, have a finite limit.
Yeah, in the case of Liouville theory, you know, in fact, several ways to take this large into a charge limit. In the case of minimal models, you're slightly more constrained because, yeah, this is our integer. I'm not sure you have the exact counterpart of Liouville theory.
Thank you.